Welcome to this video. Today we're talking about Truncated Proximal Policy Optimization, or TPPO. This paper was published a few days ago by the ByteDance team. And if you haven't subscribed to the video to my YouTube channel yet, please just take a moment and press the subscribe button, because you would definitely support me with this, and a lot of viewers haven't subscribed yet, so just take a moment and press the subscribe button. Now let's jump into the abstract to understand the overall idea. Then I will do a small recap on how PPO works, and then we look at the changes that the authors introduced in order to make TPPO more efficient. And I already said TPPO is a way to make PPO more efficient. With PPO we have a on-policy method or algorithm. They say it here. However, PPO can be time-consuming due to its inherent on-policy nature. So what does it mean? On-policy means that we are using the same policy for sampling in our environment as for updating. So in off-policy paradigm, we can use any different arbitrarily policy to sample from our environment and take updates on our target policy. On policy, we can't use an arbitrary policy for sampling in the environment. We have to use the same policy we want to update. And this makes it a little bit more inefficient, because we can't use like a replay buffer or stuff like this, because every time we make a change on our policy, we have to sample new data points from the environment. And this is why on policy method is more inefficient compared to off policy method. And they want to introduce here two ways, or actually the idea is, let's truncate a sequence so that we don't have to wait until all sequences are generated, because this can take a lot of time, especially if you think about batch training. Let's say we have 16 sentences or 16 tasks for our language model, and one task is very easy and the other one takes a long time. We have to wait until all tasks are finished. This means that we have not using our GPU very efficiently, because maybe 15 tasks are easy and just one takes a lot of time, and we have to wait until the last one is finished, and therefore we can't use the GPU so efficient. And this is what they want to change. They want to change the efficiency of the GPU memory in order to use already truncated. So they say, okay, after L time steps or L generated token, we take the sequence and already make an update on the policy. And that's the overall trick. And by using this trick, they have to change a little bit of the extended generalized advantage estimation, or it was called generalized advantage estimation, and now with their change it's called the extended generalized advantage estimation. Okay, and at the end this helps to increase the efficiency up to 2.5 times. We can see this in this image. Okay, we can see here it's a TPPO graph, and it's much faster on the clock time compared to other algorithms. So before, I would maybe just skip the introduction, because here we need to understand how PPO works. So let's jump into the idea of PPO. In Proximal Policy Optimization, or shortly PPO, we have two things to update. So we have two models. One is our policy model and the other one is our value model. The policy model is says us, given a state, how likely is the next action. Okay, so in a language for a language model, this means given the sequence, how likely is the next word, and this is our action then. And we want to increase those actions or those words that increase our expected reward. And this is what we are doing here. First of all, let's just ignore the clip here, and let's only have a view on this one. So we have like a called advantage. This advantage only says us is this action or this token better than expected? Okay, what does it mean? We have for each token we have like expected reward choosing this token, and if we choose a token that has a higher expected reward than the average, then we want to increase the probability of taking this action or this token. Okay, so if this is positive, we want to increase the ratio between the between the new policy and the old policy. Okay, so if this is just the log probabilities of taking the actions, so the multiplied log probabilities, and then we take the ratio between the old policy and the policy we want to make an update from, and if this is large, we want to increase it. And that's the only thing we have to understand here. So actually we want to maximize this surrogate objective function, and they are introducing, or in PPO we are using also a clip version. What does it mean? We don't want to increase our probability too much just because we have a good advantage. Okay, and this is why we use like a clip version of PPO. Now the next thing we have to understand is how the advantage is calculated. Maybe to understand it, I really like the way it was done in GRPO. It was the algorithm that was introduced by the DeepSeek team. There the formula looked similar to this. We take the reward for one sentence. So for one sentence, the advantage is the reward we got from the sampled divided by the mean of all the other sentence, or of all sentence. Okay, so sentence AI up to, I don't know how many sentences we have, and then divided by the standard deviation of all rewords. And this was how it was done with GRPO. So this is GRPO. So let's just think about it in a way that we have one task and we generate 10 possible answers here, and then we take all the reward that we get for those answers, and then we calculate the mean, and for each task then we take the reward minus the mean. What it actually just does is if our answers is good, then we get a higher reward than the average, and therefore we have a positive advantage. And if we have a positive advantage, we want to increase the probability of taking those actions. Okay, this is how GRPPO works with the advantage calculation. It was based on the complete sequence, but in proximal policy optimization we do it a little differently, and we are estimating the advantage using a second neural network. Let's jump to the generalized advantage estimation. Okay, so we have to calculate a so-called value function, and we have a neural network that tries to predict the value given a state. And let's understand it. Maybe we just understand value function first, and then I will go back to the generalized advantage estimation. So the value function says us, given a state or given a sentence generated up to this token, how much reward do I expect in the future? Okay, so let's say we have again a sequence, and this is our state 1 here. Then we have our value function says us how much reward do I expect from this state up to the end. And we could do it, maybe we could do this without a neural network, but if you use a neural network we get sometimes better results, because we can think about, or we could identify if the next token maybe is generated in a bad way and we think, oh, this sentence will likely not be answered in the right way. As humans, if you use ChatGPT, for example, we can see directly from like a few tokens maybe already, okay, this will result in the wrong answer. And this also can do the value function. The value function can see, okay, if you're already starting here, so I don't know, where's the Eiffel Tower located, and they start with something like Berlin, we can say directly from the beginning the probability of getting a high reward at the end is pretty low, because if the sentence starts already with Berlin, why should they go to Paris then? Okay, this is the idea of the value function, and we can calculate the value function, or we can train the value function, our neural network, just through the L2 laws. Okay, we can see this here. We have the value function up to state, for example, state t here, and we have the real reward. So let's say we have the value function st, and because we are sampling the whole sequence up to the end, we can just thumb all the rewards we are getting here. We can just thumb the discounted rewards here, and then we have the label, okay, or our target, and we call this RT. They also have the formula here, so this is not so special. So this is our target, and we calculate our target using the whole sequence. And it's a discounted reward, and at the end we are just saying, okay, let's do the L2 difference here, and then we want to minimize the loss. Again, also here we have like a clip version. Also, it's just the case we don't want to update the value function too much. I don't want to deep dive into the clip function, but the only thing we have to know is, okay, we don't want to change the parameters of the value function too much in a way that we maybe forget something because we did a huge update. Now, one important point here is we have two ways of calculating the prediction, and one way is called, or the target is called the Monte Carlo or temporals different learning, okay, and they use a Monte Carlo way to predict the value function. What does it mean? If we would take the temporal difference learning, we just making a bootstrapping. So we make one step from state 0 to state 1, we get a reward, and then, so our target would look like this. We have our reward, and this is the reward we get at directly plus the expected reward from the next state, so the expected value function from the next state, and also discounted. This would be a temporal difference learning update, and this can have a huge bias, because we make a prediction, the prediction can be wrong, and we haven't generated the whole sequence to generate our target. Therefore, we could be faster, because we not have to use the whole sequence. We can already make an update after the first step and after the second and third step. For the Monte Carlo way, we need the whole episode, so the whole sequence. But therefore, the bias is low, but the variance is high. Why is the variance high? Because we can get different outcomes because we have a lot of log probabilities we sample from it. So sometimes we are have a higher chance of getting a positive reward, and sometimes lower reward, and therefore the variance is higher. But they use the Monte Carlo way. So this target of the target we want to predict is calculated using the complete sequence, and this makes it more inefficient because we have to wait until the complete sequence is generated. And this is something they later change, and now we have a model that can give us for any state a value function which says us in the future we will generate from this state this reward. Okay, and now let's understand how we can calculate the generalized advantage estimation. Before we understand this term now in the GRE estimation, we have to understand the delta at first. And delta calculates us the temporal difference learning residual. And the temporal difference learning residual is just the error that we are making in one step. Okay, we are making one step, we get a reward, and we make a prediction from this next step, how much reward do I get. We can see this here. So I say I make one step from state 1 to state 2, and I get a positive reward with the value 2. And I also make the prediction from state 2, I think I will generate up to this. Okay, so this would also be a scalar later, and it would be maybe 1. So this would be 3. So we think by making one step and then a prediction that we generate, or that we will get at the end 3 points of reward. Our old calculation was, if we just did the prediction here, so in state 1 we thought we will just get the value 2. So we have error of 1, and therefore we have a delta of 1. This means that our action we took has brought a better reward than we thought, and this is why our advantage would be positive. Okay, this would be our first delta here. And what we can see in this term here, we don't have just one delta, but we have a lot of deltas in a row. And this is because we want to make a trade-off between using temporal different learning, so making just one step and calculating the error, and Monte Carlo, where we would take the complete sequence. So let's say we have up to S10 here, and at the end we maybe get 4 as a reward. For Monte Carlo, the residual or the error would look like this. We have 4 minus, so 4 would also be discounted here. Let's say we have a discount factor of 1, so that we can calculate it a little bit more easy. 4 minus our old prediction. Our old prediction was 2, so we get 2 as our Monte Carlo error. And for Monte Carlo we take the complete sequence, and therefore we have a smaller bias but a higher variance, because we have a lot of sampled action that we can take. This maybe sometimes we get 4, sometimes we get 3, or maybe sometimes even 10 or stuff like this. And now with this term we can do the trade-off between Monte Carlo and temporal different learning. Okay, so we have 2 hyperparameters that we can choose. The first one is our discount factor. So the discount factor is just we're discounting each reward as far as it's a reward that is maybe just 100 steps away is less counted for the current step than one that I will get directly for taking the next action. Okay, and then we have a second parameter called lambda, and lambda helps us to manage the trade-off between temporal different learning and Monte Carlo. I hope that you now understand a little bit how the advantage is calculated. At the end, it's just a way of how of making a prediction how much better our current step was than the average, and if the step was better, then we want to do this step more often. That's the most important. And the idea of making of using this lambda to make the trade-off between temporal difference learning and Monte Carlo, or the bias variance trade-off. So this is how PPO actually works. Now let's understand what kind of difference or changes we have to do in order to make TPPO and in order to make PPO more efficient. So let's understand extended generalized advantage function. They are again saying here they introduced, or in GRE we using the hyperparameter lambda, and now one important point here, as each temporal different learning's residual term becomes more heavily discounted through a bootstrapping procedure, truncation of the trajectory has a negligible effect on the actions in the front position. Okay, let's jump back to this formula to understand this. We can see here we are have a higher discount after looking more into the future. So the step 100 has a small influence on our first step, because we have this as a discount factor, and they are also saying it directly here. So this would be our discount factor after t time steps, and yeah, we can see, or this would be like the limit where it converges to. Okay, so this is why if we're looking too much into the future, the 100 step didn't have a high impact on our current advantage. And this is why they say, okay, then we could use a truncated version of it. They say it here. That means for a truncated trajectory with truncation length L, we reasonably assume that the value function of the state S and the value function of the state L minus 1 is pretty much the same. So they say it's not a big difference if I look just at the state. So if I'm at state 5, the value function of state 6 is pretty much the same as the value function of state 5. Okay, and this is why they here introduced the L instead of a T. So we using the advantage for calculating now, given a state, how much better our steps were, but we are not looking completely into the future. We are looking not up to the end, because at the end also the discount factor is pretty high. We are using just L steps in front of us, and yeah, that's all we need to understand in order to understand why it's more efficient. And the next thing is they introduce the token filtering. As if we understand this, the token filtering, we have a small view on the algorithm, and then it should be pretty clear. Maybe this at first is now not reasonably why this makes it now more efficient, but we will see it. So the token filtering strategy is also pretty easy to understand. The idea is that if we have a batch of sequences that we want to generate, or yeah, we sample in our environment, for example 16 samples in one batch, we are not waiting until all sequences are finished, all samples are finished. We are truncating it after the L time steps, and then we have some of the samples are finished because they just took a small answer, and we have some that take a very long answer, so I have a long chain of thought reasoning process, and we take only those out that are already finished for making the value update. And now there's an important point for, and yeah, we're taking the sequences out that are finished, and in the next step we would then put all the others that are not finished with the new ones to fill the empty values, because some of the sequences are finished. And now the important step here is that we then use, if the sequence is completely finished, we take it to make an update on our value function, because for our value function, again, we are using the complete sequence. So the Monte Carlo approach, we have to wait until the complete sequence finish to make a good value estimation. So the value function is just updated on a sequence when it's finished, but the policy is already updated earlier after each batch. So if we are here, we see the the time L was reached, but we haven't reached the end of the sequence for the first sample. So this is our first sample in our batch. We then make the policy updates already here with our EGRE values, but we are not using those tokens for making the value function update yet. And that's all they do in order to make it more efficient. So let's dive into the algorithm that is written here to have at the end a real understanding of why it's more efficient. So now, the first step is then we're doing it in a loop, and then we take k prompts from the last step, unfinished samples, and replace finished samples with new prompts from D. So what does it mean? Let's say we have a batch size of 4 and we generate 4, so we have to generate 4 samples, and here's the sequence length, and we can see that maybe we have a length L here. We are making the first update already after the length L, and we see those sequences haven't finished yet. This one also not, and let's say this one has finished. It's not drawn so good, so let's do it here. We can see this one finished, so in the next update we can see it here. Replace finished sample with new prompt, so this sequence here will start with a new sample, so a new task from our prompt C that we are sampling, and this one is just continuing until it finishes, and here we get a new sample. Okay, this is how it works in the first step. Then update the old policy model. This is just because we are calculating the ratio in PPO between the new logits and the old logits. In order, if the ratio is high and the advantage is high, we want to increase the probabilities. Okay, and now we collect trajectories by running the old policy in the environment until L time steps. So this is what I did actually here. So we are then running it L time step, and then we in the next step, so if we are over this loop, we are then replace the finish one. Then for each, now it's important for each finish trajectory. So we have 4, here we had 4 sequences and only one just finished after L time steps. For each of the finished one, we are calculating the discounted reward from each step. And for this sample here, we can do the update on the value function and on the policy. But for all the other sequences, we can't yet do the update. Okay, why we can't do this? Because we haven't calculated the RT, because the sequence haven't ended yet. Okay, and now we calculate the advantage estimations, and we do this on the policy tokens, and the policy tokens are then all those tokens here. So we haven't to wait until we finished the sequence. And there's also a way, they say it a little bit above, that we could use a hyperparameter, that we maybe just make the update on the tokens here, so not completely at the end, because there it's a little bit more noise. So and now for the finished sequence we are updating. So we update the policy model by maximizing the TPPO objective on all the policy tokens, and the value function we only update on the finished trajectories on the value tokens. And this is a way where we are much more efficient than before, because in the old approach with PPO, let's see how we do it then. We are not waiting up to L, a hyperparameter we choose. We are waiting until all sequence finish. This means we have 2 samples here, so this one was longer and this one was the longest, and then we have stuff like this. So we have our 4 sequences, and we can see that we are using the GPU memory here and here. We are not using it, because we have to wait until the last sequence in our batch has finished, and this is just here, and then we have a lot of memory that we are not using. This is why they say let's truncate it here. Let's use this one as a value function update, because this is already finished. On this steps we can already make a prediction, or we can already increase the probabilities of the tokens, or decrease it so we make changes on the policy, but not on the value function yet, because for the value function we need the whole sequence. So this is how TPPO works. And they call the problem that I wanted to show here, they call it due to the barrel effect, the wall time of sample generation phase is approximately proportional to maximum response length. But when we truncate the response process, suppose that L divided by L is K, where L is the actual response length and small l is the window length, then we see, okay, we have we are generating, or we have a time saving of approximately K. So at the end, I just want to highlight why does it work that we can make already an update on our policy function, even that our trajectory hasn't finished yet. And the reason is we are using this EGRE, where we just say, okay, for this state we calculate each error. So this was our temporal difference learning residual, temporal difference learning error or residual, and then we weight all the errors given a parameter called lambda. So the more it's in the future, the error will be discounted, because this is the way how we can make the trade-off between bias and variance. And so if we have like 100 steps and we have a window length of maybe 50, this means that our prediction makes like 50 steps to the future, so calculates or adds all the 50 errors on the discount lambda up, and if all the errors are positive, which would mean that our prediction was lower than the actual reward that we got, so our advantage would be positive, which means that we want to increase the probability of taking those action in the future. And yeah, we can do this even if we are not calculated the whole series, okay? And for the value function, we want to have the target. We want to have the target of the wheel reward that we got for the wheel sequence. Otherwise, if we would also do a prediction here, so let's say we make a prediction of we are just making 50 steps, so the R of 50, so the reward we got after 50 steps, plus the prediction what we get at state 50 or 51 then if we change this value function here, we would also change our target, and then it's similar to DeepQN, where we also have this problem. So if we are using here the bootstrap array and not using the complete Monte Carlo series, we would also make a here a change in our target, which makes the training makes the training unstable. Okay. So I think it was a pretty cool paper to get a view back on how the PPO and TPPO works. If you enjoyed this video, I would be really appreciate if you just take a moment and press a subscribe and like button. And yeah, if you have any ideas on new paper, I mean, I will put this paper into the video description, and you can have a look at the experience and training efficiency here for yourself. I don't want to do it too much, because it's actually very straightforward. Yeah, you can check the link out, and we will see us in the next video. Thank you.